Welcome, curious minds, to another deep dive. Today we're embarking on quite a journey into the hidden world of elements.
Yeah, not just the elements you see on a basic periodic table, but really where they're pushing the boundaries in science and tech.
Exactly. We're talking about the frontiers where inorganic chemistry is making huge impacts. Think materials in your devices, even the processes keeping us alive.
That's right. And for this deep dive, we're pulling from a really excellent source, Shriver and Atkins Inorganic Chemistry, the 5th edition. Specifically, we're focusing on chapters 24 through 27, the Frontiers section.
Our mission today, to give you a clear, structured path through these pretty advanced concepts. We'll pull out the key insights, show you how the complex stuff connects to the real world.
And we'll do it all without visuals. We'll be your audio guides, making sure you catch those aha moments, describing anything that needs a mental picture.
Think of it as your audio shortcut to understanding the cutting edge here. So let's jump right in. Okay, part 1. Solid state and materials chemistry. Building blocks of the future, really.
Right, chapter 24. And the first thing to grasp is that solids aren't, static. They're dynamic.
Yeah, we often picture them as just sitting there. But this chapter explores how we actually make them, their structures, their amazing properties, electronic, magnetic, optical, all that good stuff.
It goes beyond just perfect, simple formulas, too. So how do we make these materials? Well, sometimes it's the old school way. Direct synthesis.
You mean like baking things?
Pretty much. Mixing powders, usually oxides, and heating them in a furnace at really high temperatures. We're talking 500, maybe up to 1,500 degrees Celsius, often for days.
Wow, why so hot for so long?
You need that energy to break strong bonds in the starting materials, the lattice energies, and to get the ions moving. Diffusion in solids is slow, so high heat speeds it up, letting them rearrange into the new structure you want, like, say, barium titanate for capacitors.
Okay, but that sounds pretty brute force. Are there gentler ways?
There are. Solution methods are key here, often working at much lower temperatures. Things like the sol gel process, which we'll touch on again later.
How does that help?
You get much better mixing, like down to the atomic level, right in the liquid. So you get more uniform products, and you often don't need as high a temperature to make the final material form.
Makes sense. And for electronics, those super thin layers are vital, right?
Absolutely. That's where techniques like chemical vapor deposition, CVD or MOCVD come in. You basically deposit material from a gas phase onto a surface, building it up layer by atom layer. Crucial for chips and displays.
So we've made the solid. No, what's happening inside? You mentioned imperfections earlier.
Yes, this is so important. Defects aren't always bad. Often they're the secret sauce giving a material its useful properties.
Like what kind of defects?
Well, you have point defects, single atoms missing or in the wrong place, but also extended defects like shear planes. Imagine a perfect crystal lattice, like a stack of playing cards, and then one part of the stack slips slightly relative to the rest. That slip plane is an extended defect.
Okay, I can picture that. And how does that affect things?
It massively influences how ions move through the solid ion diffusion. Defects often create pathways or lower the energy barriers for ions to hop around.
So some ions move more easily than others.
Definitely. Small ions with low charge, like lithium, Li+8, or fluoride F, tend to be more mobile. There's a great example in the book. Silver ions, Ag plus Ev, move way faster than larger thallium ions, Tl plus L, in alpha lumina, because the silver ions can squeeze through the existing network of passages much more easily.
And this ion movement, that's not just theory, it powers things, right?
Ooh, huge practical implications. It's the basis of solid electrolytes. Think oxygen sensors in cars, or crucially, solid oxide fuel cells, SOFCs. You need ions moving efficiently through a solid material for those to work.
So better ion mobility means better fuel cells.
Exactly. Materials like YSZ, cerium-stabilized zirconia, are standard, but the push is for materials with high mobility at lower temperatures. That makes everything more efficient, cheaper, more practical.
Okay, beyond just moving ions, these solids have other cool properties. What about the third metal monoxides? Like iron oxide, nickel oxide?
Ah, yes. They show a fascinating range. Some, like manganese oxide, MnO, or nickel oxide, NiO, are insulators or semiconductors. Electrons are kind of stuck, localized on specific atoms. To conduct, they have to hop from site to site, which takes energy.
Like little particles jumping hurdles?
Kinda, yeah.
Yeah.
Sometimes the lattice even distorts around them, trapping them. But then you look at titanium oxide, TiO, or vanadium oxide, VO.
And they're different.
Totally different. They're metallic conductors. Their d orbitals overlap enough to form a continuous conduction band. It's like an electron highway. Electrons can just flow. Shows how subtle changes drastically alter behavior.
And they have magnetic properties too.
Right. MNO, FeO, Curio, RO, NEO are antiferromagnetic below a certain temperature, the Neal temperature. The electron spins on adjacent metal ions aligned in opposite directions, like tiny compass needles pointing north-south, north-south throughout the crystal.
Cool visualization. And then we get into more complex structures like spinels and perovskites.
Yeah, these are common structure types for many advanced materials. Spinels, for example, can be normal or inverse, depending on which metal ions sit in which type of site within the structure. It often comes down to which arrangement is more stable, considering things like ligand field stabilization energy.
Okay, that sounds complex but important for tuning properties. Now, something really exciting. Superconductors. Zero electrical resistance.
High-temperature superconductors, or HTSCs, yes, the dream. Materials that conduct electricity perfectly, though high temperature here still means very cold, just not as cold as traditional superconductors.
Like the famous YBCO.
Exactly. YB2Cu3O7X, the 123 compound. A key insight in designing these is often creating specific layered structures and using metals that can exist in mixed oxidation states, like copper can be Q2 and Q3. This seems crucial for the superconducting pathway.
And related but different is colossal magnetoresistance, CMR.
Whoa, yes. CMR is mind-blowing. Found in materials called manganites, often containing lanthanum and manganese. You apply a magnetic field, and their electrical resistance plummets.
How much?
By orders of magnitude. The book mentions as much as 11 orders of magnitude. It's like flipping a switch from super insulating to conducting just with a magnetic field.
That's insane. How does that work?
It's linked to something called the double exchange mechanism. Electrons hop between manganese ions in different oxidation states, MM3 and Ma, via an oxygen atom. The magnetic field helps align the spins, making this hopping much easier.
And the applications?
Data storage is a big one. Think ultra-high-density hard drives, and maybe even spintronics, a whole new kind of electronics using electron spin, not just charge.
Incredible potential. Okay, briefly, what other frontiers are mentioned in this chapter?
Well, there's work on metal hydrides, like magnesium hydride, for storing hydrogen in fuel, really important for clean energy, and colored solids, pigments.
How do they get their color?
Various ways. DD transitions in transition metals, like the blue and cobalt compounds. Charge transfer between atoms, like the yellow and cadmium sulfide. Or even intervalence charge transfer, like the deep blue of Prussian blue. And, of course, titanium dioxide, TiO2, the ultimate white pigment because it scatters light so well due to its high refractive index.
And semiconductors. Silicon is still king, but
there's ongoing work on others, like group 1216 semiconductors. And then a whole different world of molecular materials.
yeah.
Think compounds made with C60 fullerene molecules, fluorides. Some of those actually become superconducting when you add alkali metals.
Molecules acting like metals.
In some ways, yes. And even single molecule magnets, or SMMs, based on clusters like a Mn12 complex. The idea is storing a bit of data on a single molecule, ultra-dense storage.
Okay, that leads us perfectly into chapter 25, Inorganic Nanochemistry. Thinking small to get huge impacts.
Exactly. The nanoscale, roughly 1 to 100 nanometers. That's the magic realm where materials often gain completely new properties compared to their bulk versions.
And it's not entirely new, right? You mentioned stained glass earlier.
Right. Those medieval artisans using gold nanoparticles to make red glass, or silver, for yellow. They were doing nanotechnology without knowing it. The colors arise because particles that small interact with light differently.
So what's special about nanoparticles today? Let's talk quantum dots.
Few Ds are semiconducting nanoparticles.
Yeah.
They're quantum because the electrons inside are squeezed into such a tiny space. It's like the particle in a box problem from quantum mechanics.
And that squeezing changes things.
Two main things. One, the energy gap between the highest occupied and lowest unoccupied molecular orbitals. The HOMO-LUMO gap gets bigger as the particle gets smaller. Two, the energy levels become discrete, quantized, not continuous bands like in a bulk solid.
Okay, physics lesson.
Yeah.
But what does that mean practically?
It means the color of light the quantum dot emits depends directly on its size. Make it bigger, it emits redder light, longer wavelength. Make it smaller, it emits bluer light, shorter wavelength.
So you can tune the color just by controlling the size?
Precisely. Color tunability. That's why CDSE nanocrystals, cadmium selenide, are so exciting for things like super vibrant LEDs and displays. You can get really pure colors just by cooking up the right size nanoparticle.
That's amazing control. How do they make nanoparticles with such precision?
It's clever chemistry. often solution-based methods. You carefully control nucleation, the initial formation of tiny solid seeds, and then the growth of those seeds. It's like trying to grow crystals but stopping them when they're incredibly small and all roughly the same size.
Tricky. Are there other ways?
Sure, CVD, chemical vapor deposition, can be used too, and templated synthesis is really neat.
Templated, like using a mold.
Essentially, yes. You can use things like inverse micelles, tiny water droplets trapped in oil by surfactant molecules as nanoscale reaction flasks, or even etch tiny wells onto a surface with a laser. The template limits how big the nanoparticle can grow.
Molecular scale molds. And for thin films.
For ultra-precise thin films and layered structures, you use techniques like molecular beam epitaxy, MBE, or pulsed laser deposition, PLD. These let you deposit materials literally one atomic layer at a time, building up epitaxial films or superlattices with incredible control.
It sounds like we're building materials atom by atom. Can these tiny pieces put themselves together?
Often they can. That's self-assembly. Designing molecules or nanoparticles so they spontaneously arrange themselves into ordered structures using forces like metal ligand bonds. You can get complex shapes, like polyhedra, forming just by mixing the right components.
Cool. What about carbon nanotubes? They get a lot of hype.
CNTs are a fantastic example, basically rolled up sheets of graphene. They come as single-walled SWNTs or multi-walled MWNTs. They're incredibly strong and have fascinating electrical properties. Some are metallic, some semiconducting, depending on how the sheet is rolled up.
How are they made?
Usually things like CVD or arc discharge methods, often using tiny metal catalyst particles to help them grow. And tons of potential. Reinforcing materials, making polymers stronger, chemical sensors, electronics, even tiny tools, like the idea of nanorobotic spot welding.
Nanobots. Okay, what else is happening at this scale?
We can create quantum wells, thin layers of one semiconductor sandwiched between layers of another, and superlattices, which are repeating stacks of these layers. These structures manipulate electron behavior in specific ways, leading to things like quantum cascade lasers.
And materials with pores.
Yes, mesoporous materials.
Yeah.
These are made using surfactant molecules as templates to create solids with highly uniform pores, typically between 1.5 and 10 nanometers wide. Great for catalysis, letting reactants get in and products get out easily.
Mixing nano-inorganic with other stuff.
Absolutely. Inorganic, organic nanocomposites, like adding carbon nanotubes to polymer nanocomposites, or PNCs. Even a small amount can dramatically increase strength. The book mentions SWNTs making polymers potentially 100 times stronger than steel for their weight.
Wow. And learning from nature.
That's biomimetic nanocomposites. We try to copy nature's tricks. The classic example is the red abalone shell nacre, or mother of pearl. It's calcium carbonate, but arranged in intricate layers with biopolymers, like bricks and mortar. This structure makes it incredibly tough. We learn a lot by studying how organisms build these sophisticated inorganic materials.
So the nanoscale is already making a difference.
Definitely. There are examples like CO2s nanocrystals on carbon nanotubes being used as highly sensitive biosensors for glucose, or Syria nanocomposites helping clean up pollutants like arsenic and chromium from water. Tiny structures solving big problems.
Right. Let's shift gears to Chapter 26, Catalysis, speeding up chemistry.
Exactly. Catalysis is all about making reactions go faster or making them choose a specific path, selectivity, without the catalyst itself being used up. It works through a catalytic cycle where the active catalyst species gets regenerated.
There are different types, right? It's homogeneous first.
Yeah, homogeneous catalysis means the catalyst is in the same phase as the reactants, usually dissolved in a liquid. This often allows for really fine-tuning and understanding the reaction mechanism in detail.
Any standout examples?
Oh, absolutely. Alkene metathesis is a huge one. It basically swaps partners between carbon double bonds. The development of catalysts like Grubb's catalyst was revolutionary for synthesizing complex molecules and polymers. It gives chemists incredible control over building carbon frameworks.
And adding hydrogen, hydrogenation.
Still very important. Wilkinson's catalyst is a classic example. But even more sophisticated is enantioselective hydrogenation.
Making just one mirror image version of a molecule.
Precisely. Many molecules, especially drugs, are chiral effacement. They exist as left and right-handed forms. Often only one form works. Using catalysts with special chiral ligands, like DIPAMP used in making L-DOPA for Parkinson's, allows chemists to make almost exclusively the desired enantiomer. It's vital for pharmaceuticals.
So these catalysts are like molecular machines with incredible precision. What about big industrial processes?
Huge ones rely on catalysis. Hydroformylation adds CO and H2 across an alkene double bond to make aldehydes, which often get turned into alcohols for plastics and detergents. It uses cobalt or rhodium catalysts, and ligands can steer the reaction towards linear or branched products.
And the Wecker process.
That turns ethene into ethanol, acetaldehyde. Uses palladium chloride, but the clever part is using copper to continuously reoxidize the palladium back to its active state, a classic example of coupling catalytic cycles.
Palladium seems important.
Hugely important, especially for CC bond-forming reactions. Things like the Heck, Still, and Suzuki reactions are workhorses in organic synthesis, letting chemists stitch together complex molecules. They often involve similar steps like oxidative addition and reductive elimination at the palladium center.
Okay, how about heterogeneous catalysis, solid catalysts?
Right here, the catalyst is usually a solid, and the reactants are gases or liquids.
Mm-hmm.
The name of the game is high surface area and porosity,
Why is surface area so key?
because the reaction happens on the surface of the catalyst. Materials like gamma lumina or silica gel aren't dense solids. They're full of tiny pores and channels. Imagine a sponge or gravel. This creates enormous internal surface area. The book mentions potentially a tennis court's worth per gram.
Wow. And what's special about the surface itself?
The surface has active sites. On oxides like alumina, you can have acidic sites, like Brunstad acid OH groups or Lewis acid-exposed metal ions, and basic sites, like surface oxygen ions. These can grab onto molecules and help them react.
And with metal catalysts.
Molecules undergo chemisorption. They form actual chemical bonds with the metal atoms on the surface, like MCO or MH. This activates the molecule, making it more
Oh,
reactive.
it's a balancing act.
Exactly, the Goldilocks principle. Adsorption needs to be strong enough to activate the reactant, but weak enough so the products can leave and free up the site for the next cycle. Too strong, and you poison the catalyst. That's why only certain metals work well for specific reactions.
Are these solid catalysts as precise as the homogeneous ones?
Often less so. Real catalyst particles have different crystal faces exposed, edges, corners, defects, non-uniform sites. This variety means you sometimes get a mixture of products, lower selectivity compared to a well-defined homogeneous catalyst.
Let's talk industrial giants. Hopper Bosch.
The big one,
Yeah.
making ammonia NH3 from nitrogen N2 and hydrogen H2 uses an iron catalyst, boosted with promoters like alumina and potassium salts. The huge challenge is breaking the incredibly strong triple bond in N2, which requires high temperatures and pressures even with the catalyst. It literally feeds billions of people.
What else?
The contact process for making sulfuric acid, oxidizing SO2 to SO3 using a vanadium-based catalyst. And alkene polymerization, making plastics like polyethylene and polypropylene using Ziegler natocatalysts, often titanium-based, or newer metallocene catalysts, which offer better control over the polymer structure, its tacticity.
And connecting electricity and catalysis.
That's electrocatalysis. Catalysts here help reduce the overpotential, the extra voltage you need to push a slow electrochemical reaction, like splitting water into hydrogen and oxygen. Materials like platinum black or ruthenium dioxide, or RuO2, are used, especially important at things like PE in fuel cells to make them more efficient.
Okay, final frontier for today. Chapter 27, where inorganic chemistry meets life. Bio-inorganic chemistry.
Yeah, this is about how living systems harness inorganic elements. It's not just carbon, hydrogen, oxygen, nitrogen metals, and other elements play absolutely critical roles.
Structural roles, but much more too.
Oh, way more. Catalysis, signaling, transport, defense. Life is incredibly clever at using the properties of different elements. Sodium, potassium, calcium, magnesium are major players, plus loads of trace metals like iron, zinc, copper, manganese.
And they're not just floating around.
No way. Their concentrations are tightly controlled, often very different inside versus outside cells, like Na plus outside, K plus inside. And they're almost always interacting with biological ligands, proteins, DNA, small molecules in very specific ways. These interactions define their function.
Let's talk transport, getting things across cell membranes. Sodium and potassium.
Absolutely vital. Cells use energy-hungry ion pumps, like the famous Na plus K plus ATPase, to maintain steep concentration gradients. Lots of sodium outside, lots of potassium inside. This gradient is like a battery powering other processes.
But how do they let one ion through but not another? They seem pretty similar.
That's the magic of ion channels. Take the K plus channel. It lets potassium through thousands of times better than sodium, even though they're similar in size. The trick is a selectivity filter, lined with carbonyl groups from the protein backbone.
How does that work?
It's perfectly sized to interact with the dehydrated potassium ion, stripping off its surrounding water molecules. A dehydrated sodium ion is actually slightly smaller and doesn't fit snugly enough to make those favorable interactions. It's an amazing piece of molecular engineering based on size and coordination chemistry.
Incredible. And calcium, that's a signal.
A key intracellular messenger. Its levels inside cells are usually kept extremely low, but when a signal comes, channels open, calcium floods in, and it binds to proteins like calmodulin.
What does calmodulin do then?
Binding calcium changes calmodulin's shape, and this new shape allows it to interact with and activate other enzymes, like no synthase, triggering downstream effects. It's a rapid on-off switch controlled by calcium levels.
What about zinc? Is it just structural?
It plays structural roles, yes, but also crucial regulatory ones. Think zinc fingers. These are protein motifs where a zinc ion holds a loop of the protein together, typically coordinated by cysteine and histidine residues.
And these fingers do what?
They are shaped perfectly to recognize and bind to specific sequences of DNA. This allows proteins containing zinc fingers to act like switches, turning genes on or off, controlling transcription. Fundamental stuff.
Iron seems critical too, but also dangerous.
Exactly. Essential for oxygen transport and electron transfer, but free iron can generate harmful radicals. So life has elaborate systems to handle it.
Right.
Bacteria use cytophores to scavenge iron. We use transferrin to transport it in blood and ferritin to store it safely inside a protein shell.
And its roles, oxygen transport.
That's hemoglobin in our red blood cells, with its iron porphyrin heme group binding O2. Other creatures might use copper-based hemocyanin. For moving electrons around, especially in respiration and photosynthesis, you have cytochromes, also heme-based, and iron-sulfur clusters.
Iron-sulfur clusters, like little cubes or squares of iron and sulfur atoms.
Exactly, like 2FD2S or 4Fe4S units held within proteins. They act as electron relays. And don't forget blue copper centers in proteins like plastocyan and copper, held in a special strange geometry that makes electron transfer super fast.
Okay, life uses metals for transport and structure. What about catalysis, the enzyme machine shop?
Oh, metals are at the heart of many enzymes. Carbonic anhydrase uses zinc to rapidly convert CO2 and water to bicarbonate, essential for getting CO2 out of tissues into the blood. It's incredibly fast.
Dealing with dangerous oxygen byproducts.
Yep. Catalase uses iron in heme to break down hydrogen peroxide, H2O2. Superoxide dismutase uses copper zinc, or sometimes iron or manganese, to neutralize the superoxide radical, O2, absolutely vital defense mechanisms.
And enzymes that use oxygen itself.
Things like cytochrome P450 and other heme iron enzymes are amazing. They activate oxygen to insert an oxygen atom into organic molecules crucial for breaking down toxins or synthesizing hormones. Methane monoxygenase uses iron or copper to convert methane into methanol.
Any other unusual metals? Cobalt?
Cobalt is special. It's at the center of cobalamin, vitamin B12. The enzymes using it, like coenzyme B12, do fascinating chemistry, including methyl transfer reactions and complex radical-based rearrangements. B12 is one of the very few examples of a stable metal-carbon bond in biology, an organometallic compound made by nature.
Even heavier elements.
Molybdenum and sometimes tungsten are used in enzymes that perform oxygen atom transfer reactions, often involved in metabolizing small molecules containing sulfur or nitrogen or even carbon monoxide.
Life builds hard structures too, right? Biomineralization.
Right. Organisms sculpt inorganic materials. Think calcium carbonate in seashells and coral skeletons. Some bacteria make tiny magnetic crystals of magnetite, F3O4, to use as compasses. Plants use silica for strength and protection.
And it's not just dumping mineral.
Not at all. It's highly controlled crystallization, often involving specific proteins that guide crystal growth, shape, and orientation. Again, look at nacre mother of pearl. That layered structure is incredibly sophisticated and tough, far beyond simple calcium carbonate.
Finally, inorganic chemistry's role in medicine.
Huge impact. Chelation therapy uses ligands like dysferyl to bind and remove excess toxic metals like iron overload from blood transfusions.
Cancer treatment.
The landmark drug is cisplatin, cis-PTCl2-NH32. It's a simple platinum compound, but it binds to DNA in cancer cells, kinking it and interfering with replication.
And the shape matters.
Critically.
Yeah.
The cis isomer is active, the trans isomer is essentially inactive. A beautiful example of structure-activity relationships. Other metals are used too. Gallium compounds target some enzymes. Bleomycin uses iron to damage DNA.
Arthritis.
Gold compounds, surprisingly. Things like ornithine have been used to treat rheumatoid arthritis, though their exact mechanism is complex, maybe interfering with enzymes or reactive oxygen species.
And seeing inside the body,
Yeah.
imaging.
Yes. Gadolinium complexes are widely used as contrast agents in MRI scans. The paramagnetic Gd affects the water-proton relaxation times, making tissues show up more clearly. For nuclear medicine, SPECT imaging, complexes of radioactive technetium-99 are designed to target specific organs, heart, brain, bones, allowing doctors to see their function. So where is bio-inorganic chemistry headed? So many directions. Understanding ion channels better for neuroscience, mapping how zinc moves in the brain, metaloneurochemistry, engineering crops with better iron content, developing bio-inspired catalysts that mimic enzymes to do difficult reactions efficiently, like methane activation or water splitting for hydrogen fuel, learning from life's chemistry to solve human problems. Hashtag tag outro.
Wow, what a journey. We've gone from baking ceramics at furnace temperatures to watching single ions slip through channels in our cells, from superconductors to quantum dots to life-saving drugs.
It really underscores how controlling matter at the atomic and molecular level using the principles of inorganic chemistry unlocks just incredible properties and functions. It's happening everywhere.
And for you listening, think about it. The chemistry we've discussed underpins the technology you use, the energy systems we need, even the biological processes within you right now, from the toughness of a shell to the action of a cancer drug. It's all inorganic chemistry at its frontiers.
So the question to leave you with is, what's next? What unexpected combination of elements or what clever biological trick we haven't fully understood yet will define the next frontier in materials, energy, or medicine?
A great question to ponder. Thank you so much for joining us on this deep dive through the frontiers of inorganic chemistry. We hope it's given you some valuable insights and maybe sparked some of your questions.
Thanks for tuning in.
From the entire team here at The Deep Dive, thanks again, and we'll catch you next time.